All right, hello everybody, and welcome to the Morrison Planetarium. My name is Katie. I use she, her pronouns, and I will be your presenter for our tour of the universe. We are going to be using a program today called OpenSpace to explore the universe, and this is a free open source software that uses data from telescopes both on the ground and in space, as well as spacecraft that we send to other worlds. So everything we're going to see today is based on actual data. We're not going to see any artist's renditions or anything like that. So if you have any questions about that program, you can come and talk to me after the show. Before we get started on the show, I do have a few housekeeping announcements. First, please turn off or silence all electronic devices, especially those cell phones. Keep them tucked away for the duration of the show. It's going to get pretty dark in here, and any excess light is going to be a distraction to those around you and ruin all the hard work your eyes have done adjusting to the darkness. There's also no filming or photography during the show. There's no eating or drinking in the planetarium. And for your safety, we ask that you remain seated for the duration of the show, as these stairs can be difficult to climb in the dark. We also don't want you blocking one of our projectors and creating a U-shaped hole in the universe. If for some reason you do need to leave during the show, please exit to the top of the stairs. Go up, not down. If at any time you feel any symptoms of motion sickness, such as nausea or dizziness, we recommend that you sit back, close your eyes, remind yourself that you're sitting in a stationary theater and not flying through space, and the feeling should pass. All right, last call for cell phones. Please make sure those screens are dark. And we're going to get started now on our tour of the universe. All right, we are going to start our tour off at a very familiar place, our home, planet Earth. Isn't it lovely? This is where almost all of human history has occurred, and where all human beings live. Well, almost all human beings. At any given time, scientists from countries all around the world are aboard the International Space Station, living and working together. So we can see the orbit of the space station here is this yellow line. Let's zoom in on it to get a closer look. Now, the space station is about the size of an American football field or 3 blue whales across. Perhaps you saw our blue whale skeleton over by the rainforest. That should give you some sense of the size. So we got 3 blue whales. Now, the space station orbits only 225 miles above the Earth, circling our planet once every 90 minutes. That means that it's traveling over 17,000 miles per hour. This is the part where I make a bad joke. I wouldn't want to have to pay that speeding ticket. Thank you. Now, this is the furthest humans currently travel into space, but it's not the furthest we've ever been. Between 1969 and 1972, human beings went to the moon, and 12 NASA astronauts even got to walk on its surface. So let's go take a closer look at our partner in space. All right. So the side of the moon that we normally see when you look up at the moon, we call that the near side of the moon. The moon is tidally locked to the Earth, meaning that the period of its rotation, 1 lunar day, is equal to the period of its orbit, 1 month. Because of this, we only ever see this one side of the moon that we are coming in and looking at now. All right, this is the side we're most familiar with. So it's characterized by these big dark patches called maria, or the singular is mare, meaning sea in Latin. So what astronomers once thought were bodies of water, we now know to be basalt plains. These are the results of ancient lava flow across the moon's surface. It wasn't until 1959, when the Soviet Union sent the spacecraft Luna 3 to the moon, that humans got a look at the far side, or the side facing away from Earth. So let me turn off night, because currently this side is facing away from the sun, but I'm going to turn the nighttime off so that we can see it better. There we go. You might notice that this side of the moon looks a lot different from the near side of the moon. It's got a lot more craters, which means that there wasn't any lava flow on this side of the moon to fill the craters in. These craters remain unchanged from when they formed, since there's no weather on the moon to cause erosion. We can learn a lot about the moon's history and the history of the solar system more generally by studying these craters. And the moon is 240,000 miles away from Earth, and it took the Apollo astronauts over 3 days to get there, traveling at 25,000 miles per hour. And we're starting to get to speeds and distances that are hard to imagine. So let's switch to a more useful unit of measurement. One of the ways astronomers describe distances is in light years, light minutes, light seconds. This tells us how far light, the fastest thing in the universe, travels in that given unit of time. The moon is 1.3 light seconds from Earth, meaning that it takes light that's reflected off the moon 1.3 seconds to get to Earth. It also means that when you look up at the moon, you're seeing it as it was 1.3 seconds ago. And that's an important thing to remember as we travel farther and further away from Earth during our tour. The farther away something is, the further into the past we are seeing it. And the moon may be the furthest that humans have been, but we've sent spacecraft like rovers, probes, and landers even further. Now we're moving beyond the realm of Earth and out into our solar system. At the center of the solar system is our star, the sun, which is about 8 light minutes away from Earth, or 93 million miles. Our sun is a middle-aged star at about 4.5 billion years old. Orbiting around the sun, among other things, we have the 8 major planets: Mercury, Venus, Earth, Mars, Jupiter, Saturn, Uranus, and Neptune. Now you might be asking yourself, what about Pluto? Why didn't she mention Pluto? It's my favorite planet. Well, Pluto was reclassified as a dwarf planet some years back, and for good reason, I think. So I'm going to put its orbital path up now. It's going to be in a lighter blue color. And we can see some of the things that make it a little bit different. So one thing you might notice is that its orbit isn't in the same plane as the orbits of the major planets. It looks like it's kind of tilted with respect to the rest of them. It's also a different shape. The major planets orbit in almost perfect circles, but Pluto's orbit is much more elliptical, or egg-shaped. It even gets closer to the sun than Neptune at certain points in its orbit, so it's not staying in its own lane. It turns out it fits in a lot better with these objects. So these are the orbital paths, the trails of the trans-Neptunian objects, or Kuiper Belt objects, small icy bodies like comets and dwarf planets orbiting the sun beyond Neptune's orbit. In recent years, we've discovered some dwarf planets like Eris that are even bigger than Pluto. So I think if Pluto could feel, it would be happy with its new classification. Instead of being the smallest planet in the solar system, it's everybody's favorite dwarf planet, or at least the most well-known dwarf planet. So Pluto's orbit is about 10 light hours across. But it took the New Horizons spacecraft 9 years to travel there from Earth. So speaking of New Horizons, let's see how far human-made objects have traveled. New Horizons was launched in 2006, reached Pluto back in 2015 and has been traveling through the outer reaches of the solar system ever since. In the 1970s, we launched Pioneers 10 and 11 and Voyagers 1 and 2 to visit and take pictures of the gas giant planets. They are all traveling fast enough to escape the sun's gravity and leave the solar system behind. And even though they've been traveling for about 50 years, Voyager 1, which has traveled the farthest, still hasn't traveled as far as light makes it in one day. So now let's get back in our spaceship and fly out even further, leaving the solar system behind and heading out into interstellar space, the space between the stars. The nearest star, Proxima Centauri, is 4 light years away. So compare that to the 1 light day that Voyager 1 has traveled. So now I'm going to turn on something called the radiosphere. Now this is not an actual object that you would see if you were to travel this far out into space. It's a representation of the furthest distance that human influence can be felt. In the 1930s, humans started emitting strong electromagnetic radiation in the form of radio waves, TV and radar signals, and atomic weapons detonations. These signals were strong enough to leave Earth. They travel at the speed of light, which means that the earliest signals have traveled about 90 light years. So that's the radius of our sphere here. Maybe someone out there has detected our signals. But where could that someone be? Each of these blue markers indicates a star where astronomers have discovered 1 or more exoplanets, a planet orbiting a star other than the sun. The ones within the radiosphere are the only ones that have had a chance of detecting our radio signals. But there are so many more beyond that. Astronomers have discovered over 5,000 exoplanets, and they're still finding more. We now believe that most stars have planets orbiting around them, making our solar system the rule, rather than the exception that we once thought it was. One of the big topics of research these days is finding Earth-like planets with suitable conditions for life. We wouldn't be able to travel to these planets, since it would take thousands of years to get there with our current technology, but it's nice to know that they're out there. And now let's go beyond our stellar neighborhood and see what lies outside of it. Our little solar system lives in one of the spiral arms of the Milky Way galaxy. This is a computer model of what we think our galaxy looks like from the outside. We can't take an actual picture of it because we haven't traveled this far out into space, but we can use the data we collect from here on Earth, as well as our knowledge of other galaxies, to make a pretty good map. At the center of the Milky Way is a supermassive black hole called Sagittarius A star. A black hole is a point in space that is so massive and so dense that not even light can escape from it if it gets too close. Most black holes are the remains of huge stars that have exploded. Supermassive black holes are much, much bigger than that and reside at the centers of galaxies. Sagittarius A star is about 4 million times more massive than the Sun, and all that mass is contained within a space with a radius only 30 times the radius of the Sun. Now, you may have heard about the detection of a gravitational wave background in the news recently, which is very exciting. And it's likely that these waves come from the mergers of supermassive black holes, like Sagittarius A star, though they haven't determined that for certain just yet. But a galaxy is more than just a black hole, though. The Milky Way contains more than 300 billion stars, which means there are likely billions of planets out there. It's 130,000 light years across. The amount of time it takes for light to travel from one end to the other is equal to the length of the history of the human species. But that's just our own galaxy. 2 million light years away is the Andromeda Galaxy, our nearest major galactic neighbor, excluding dwarf galaxies. The Milky Way and Andromeda are hurtling towards each other and will collide in about 5 billion years, creating a new combined galaxy nicknamed Milkdromeda. And that is what they're calling it. I didn't make that name up for laughs. Now, you don't have to worry about this collision, though. Galaxies are mostly empty space, so there isn't much risk of our solar system colliding with another star. Also, life on Earth will likely have already ceased to exist by then because of the sun's increasing size and temperature in its old age. Milky Way and Andromeda are only 2 of the many hundreds of billions of galaxies that comprise the known universe. As we zoom out, all the dots you're seeing represent not stars, but galaxies, each containing hundreds of billions of stars. Galaxies aren't evenly spaced. They tend to cluster together in groups. Andromeda and the Milky Way are part of what we call the local group, which in turn is part of a bigger cluster called the Virgo supercluster. So right now, what we are looking at are really just data points. So showing us where we can find where we know galaxies to be. But we do actually have pictures of galaxies and galaxy clusters. For example, we have this image. So this is the first deep field image taken by JWST. It shows us a galaxy cluster that's 4.6 billion light years away from Earth. This image contains thousands of galaxies, 84 of which are some of the youngest galaxies we've observed. So they're existing between 200 and 400 million years after the Big Bang. Not everything in this image is part of the cluster, though. So you can see those really bright objects, like the one towards the center of the image. That's a star in our own galaxy. That's in the same line of sight as the cluster. We can also see objects that are behind the cluster, like this space bacon here, up in the top right corner, kind of. So it's not actually bacon. This is a galaxy that appears stretched out due to an effect called gravitational lensing. According to Einstein's theory of general relativity, matter causes space itself to curve, and the light from behind these giant galaxy clusters gets magnified and distorted because of this curvature. Studying the effects of gravitational lensing can teach us a lot about galaxy clusters. In particular, they help us study dark matter, that mysterious invisible matter that makes up about 25% of the universe. Now, there's a lot more we could talk about in this image, but we still have a bit more universe to see. So let's head back to our galaxy data here. Now, one thing, do you notice about this data is that it's kind of a funny shape, like an hourglass. It makes it look like we are at the center of the universe, and we're actually not. In fact, there is no center of the universe. It just looks like that because of the limits of our observations. We can only see so far in every direction, so we are at the center of our observable universe. And the reason we have these big dark patches, the reason it's sort of hourglass shaped, is that the gas and dust of the disk of the Milky Way is blocking our view in those directions. Hopefully someday soon we'll have the tools to peer through that dust and make a more complete map. What we see, though, will probably look very similar to what we see in every other direction. Now, moving out further still, we're going to start to see some red dots at the edges of our hourglass here. And these represent quasars, or active galactic nuclei. These are the cores of young galaxies, where gas is falling into the central black hole and extremely energetic electromagnetic radiation is being released. These are all billions of light years away, meaning that they existed in the earliest stages of the universe, when galaxies were just beginning to form. If we could see what they look like right now, they might look a lot like our own galaxy. But we'll have to wait a few billion years to find out for sure. And now let's keep going even further still. What we're looking at here is called the cosmic microwave background. It's basically the universe's baby picture. Isn't it cute? This light was emitted about 380,000 years after the Big Bang, which happened about 13.8 billion years ago. This is an image we get using radio telescopes. It shows us light that we can't see with our eyes. Another way to think of it is as a temperature map. On average, this radiation currently has a temperature of about minus 455 degrees Fahrenheit, or minus 270 degrees Celsius. So just a couple degrees above absolute zero. But there are tiny fluctuations in that temperature. Brighter areas are hotter, denser regions, and darker areas are cooler regions. Cosmologists use these fluctuations to learn about how the earliest structures of the universe formed. This radiation comes from all directions, all the time. But don't worry, it's not dangerous. It's very low energy. If you've ever seen static on an old television, some of that static is coming from the cosmic microwave background. So this is as far as we go. There's no light to see past this point. If we want to directly observe anything older than this, we'll have to use some other method of observation. So for now, let's head home. People often ask me, as a planetarium presenter, what my favorite planet is, and I give them what seems like a boring answer. Earth. Earth is magnificent, and humans are perfectly suited for it. It provides air that we can breathe, water that we can drink. Its atmosphere protects us from harmful radiation from the sun. It provides trees whose shade we can sit under, flowers for us to smell, cats to pet, and dogs to play with. In the scheme of things, it may seem like a small, meaningless speck of dust, but to us, it's our only home. So when you next look up at the night sky, I hope you remember just how special our home truly is. And here we are again. Home sweet home, there's no place like home. That is our show. Thank you so much for joining us.